Welcome to G Fun Facts Online, where we explore the most mind-boggling questions about our universe. Today, we're diving deep into a cosmic mystery. Why is there something rather than nothing? I mean, look around. You, me, the planets, the stars. It's all made of matter. But according to our best theories of the universe's birth, the Big Bang should have created equal amounts of matter, and its spooky twin, antimatter. When matter and antimatter meet, they annihilate each other in a flash of energy. So if they were created equally, they should have wiped each other out, leaving behind a universe filled with just light. Yet here we are. This profound imbalance, known as the matter-antimatter asymmetry, is one of the biggest puzzles in physics. Our current rulebook for particle physics, the Standard Model, does try to explain this. It predicts a tiny difference in how matter and antimatter behave, a phenomenon called charge parity violation, or CP violation for short. Think of it like a slightly loaded die. Matter and antimatter aren't perfectly symmetrical in their actions. The problem is, the amount of CP violation the Standard Model predicts is way too small, orders of magnitude too small, to explain why matter completely dominates our universe. This huge gap tells us something big is missing, hinting at new physics beyond what we currently understand. And excitingly, recent breakthroughs are giving us fresh clues. For a long time, scientists had only seen CP violation in particles called mesons. But they suspected that baryons, particles like protons and neutrons that make up almost all the visible matter we see, should also show this lopsided behavior. And guess what? In March 2025, a major announcement came from the LHCb experiment at CERN. They found overwhelming evidence of CP violation in a baryon called the Beauty Lambda baryon. By smashing protons together at incredible speeds in the Large Hadron Collider and sifting through mountains of data, they observed that the Beauty Lambda baryon and its antimatter partner don't decay at exactly the same rate. We're talking about a difference of about 2.45% in their decay rates, a result so statistically significant, 5.2 standard deviations, that physicists confidently call it a discovery. This was the first time CP violation was definitively seen in baryons, opening up a whole new playground to study this asymmetry. Now, while the Standard Model does predict some CP violation in baryons, its current predictions aren't precise enough for a head-to-head comparison with this new LHCb measurement. But the crucial point remains. Even with this new observation, the total CP violation we know about from the Standard Model still isn't enough. The hope is that by finding more of these asymmetries in different particles and measuring them with ever-increasing precision, we'll find deviations that point to new, undiscovered sources of CP violation. And the LHCb team didn't stop there. They also found hints of CP violation in how other beauty particles, called beauty hadrons, decay into another type of particle called carbonium. This particular finding, from the decay of a beauty meson into a J/PA particle and a pion, had a significance of 3.2 standard deviations. While not a full-blown discovery yet, it's another intriguing piece of the puzzle. Earlier studies had also hinted at similar asymmetries in other baryon decays and in particles containing charmed quarks. The more places we see these subtle differences, the better our chances of cracking the Standard Model's limitations. But the search isn't just happening at the LHC. Another fascinating area of research involves neutrinos, those ghostly, superlight particles that barely interact with anything. The T2K experiment in Japan has been studying how neutrinos change their flavor as they travel. They shoot beams of muon neutrinos and muon antineutrinos from one side of Japan to a detector 295 kilometers away on the other side. By comparing how these neutrinos and antineutrinos transform into electron neutrinos and electron antineutrinos, they're looking for differences in their behavior. In 2020, T2K released results showing the strongest evidence yet that neutrinos and antineutrinos might indeed behave differently. This could mean that the lepton sector, which includes neutrinos, contributes to the matter-antimatter imbalance through a process called leptogenesis. If this is confirmed, and if the effect is large enough, it could be a huge step towards solving the mystery. T2K is now in its second phase, aiming for even more precise measurements. So why do these tiny deviations matter so much? Because the Standard Model, for all its successes, is incomplete. It can't explain gravity, dark matter, dark energy, or this very matter-antimatter asymmetry we're talking about. The fact that its predicted CP violation is too small is a major clue that there's more to the universe than it describes. These new observations of CP violation in baryons, and potentially in neutrinos, are like breadcrumbs leading us towards this new physics. They could be the signatures of undiscovered particles or forces that are adding to the CP violation in ways our current theories don't predict. Think about it. Back in 1967, physicist Andrei Sakharov outlined what conditions would be needed for a universe to start with equal matter and antimatter and end up dominated by matter. These include processes that change the number of baryons, violations of CP symmetry, which we're seeing, and interactions happening out of thermal equilibrium. The Standard Model has bits of these, but the observed strength of CP violation is the missing ingredient. The quest to find these new sources of CP violation is a top priority for particle physicists worldwide. Experiments like LHCb will keep crunching data from the LHC's current and future upgraded runs, which will provide even more data to analyze. Meanwhile, other experiments are probing antimatter's fundamental properties. The BASE collaboration at CERN, for instance, has shown that protons and antiprotons have identical charge-to-mass ratios to an incredible degree of precision, and that antimatter seems to fall under gravity, just like matter. Discoveries of new, heavy antimatter nuclei also help us understand antimatter better. Every new observation, every slight deviation from what the Standard Model predicts, is a vital clue. These findings aren't just about esoteric particles. They're about understanding the very fabric of reality and answering that fundamental question: why are we here? Why is there something instead of nothing? The exciting part is, with these new hints and ongoing research, the next big breakthrough might be just around the corner, potentially ushering in a whole new era of physics. Thanks for tuning in to G Fun Facts Online. Join us next time as we unravel more wonders of the cosmos.